This is the network science course, and today we are going to discuss the 14th chapter of Mark Newman's book, which is entitled as Models of Network Formation. So today we are going to talk about the so-called generative network models, and so the idea behind this discussion is that we would like to have some simplified or simply enough mathematical models for understanding how networks are getting formed in nature, basically. And the main reason for getting such a model is very simple, because we would like to, so if we have such a model, then we can do some experiment with it, and with the experiments we get much better understanding why and how things are happening out there. And of course, with the mathematical model, we can also try out different scenarios, different cases which, for example, we couldn't do in real world. And so I think you get the idea. And so one of the best known examples of generative models is the so-called preferential attachment. And this is strongly related to the earlier discussion of us with respect to the so-called power law degree distribution. Hence, what we are going to discuss are the corresponding models, which is first the so-called price model, and the other one which was proposed by Barabashi and Albert. So today we are going to discuss mainly the price model. And referring back to last week's lecture, we have seen that lots of networks in real world, they are following the power law degree distribution. And so Price, he was a scientist, and he was interested in the so-called citation networks of scientific papers, and he was one of the first ones who pointed out that in these networks, in these kind of networks, citation networks, the nodes degree as considered as a distribution, they are following they are following power law functions or power law structure. And so he in fact Price was himself inspired by an economist called Herbert Simon. And Simon was the first economist who pointed out the famous nowadays well-known phenomena which is called the rich get richer, and that also corresponds to the power law distribution, of course. And so back to Price, he gave so he was basically with his kind of contributions with respect to the citation networks, he was basically giving the foundation to the so-called scientometrics as a scientific area. And if you want, as a homework, you can also check out maybe on Wikipedia some kind of related measure which is called as Hirsch index or H index, okay, regarding the citation. And so in a citation network, by the way, what is the point is that the nodes, of course, they are papers, and a node is connected with a directed edge to another paper if that original paper cites this other paper. So this other paper appears in the list of references. And so back to Price again. He was giving the name or the mechanism So he was giving the name of cumulative advantage, and this is basically the same thing what then later on Barabashi and Albert started to call as preferential attachment. And so the main reason behind this cumulative advantage or preferential attachment thing is the following model. That so this is what we are now laying down, is that so the papers, let's assume that they are published continually. Okay, so not necessarily a constant rate, but so every now and then a new paper is appearing, okay, as normal. And these newly appearing papers, they are citing the previously existing papers, and there is no disappearance, so there is no paper disappearing from this network. And so now we are going to denote with C the number of papers on average one paper cites. Okay, so we can you can imagine that C is, let's say, equal to 10, for example, and then by that we are expressing the fact that that on average, so on average and as an expected value, the number of references in a certain paper is equal to 10. So what does it mean in terms of graph theory? Of course, it means that on average a node's out degree is an average out degree is equal to C. Okay. Now there is a crucial assumption in the price model, which is the following: that a paper which appears as a new paper, basically. It's citing the previously published papers, but in a kind of a random way, but not absolutely, so not uniformly at random, but those papers which already got higher number of citations, so they have larger number of in degree, then those papers, they have larger probability to get even more citations. Okay, so this is the rich get richer effect. And of course this is a very basic model, so it doesn't question which papers are the most relevant topically, which papers are which papers are the most original ones or the best written papers, or if there is any difference between research articles and reviews. So all these questions are neglected here. So this is a very simplified representation of citation process, but you will see later on that that it's basically capturing the procedure very well. And so of course the problem with the whole setup so far is the following: that if there is a paper which doesn't get a citation, then of course later on in time the probability that it will get a certain point later it will get a citation is basically tending to zero. So practically it becomes a zero probability to get citation. And then, as usual, the standard trick for this case is that we give a free citation to each and every paper. So that's just a default number. We can set it up to 1 or 2 or 3. It could be even maybe a fractional number. It doesn't. So it just needed there for technical reason, only to avoid the case that if a paper has a 0 in degree, then basically in the model it will get 0 in degree forever. Okay, so A is going to be the number of free citations, which could be equal to every node. And I think in the second or third lecture, we already mentioned that this kind of citation network in fact leads to a directed acyclic graph. And the kind of proof was that if you start drawing this kind of graph in such a way that the new papers are appearing in only the let's say the top part or bottom part, it doesn't matter where the time is flowing or going on, and then you just connect the nodes in a backwards way, then basically you never get a cycle, and the graph itself is directed. So this is the reason, or the very short explanation, why we get a dog here.